Hello everyone, welcome to my talk. And my name is Chen Wei from the University of Wisconsin-Madison. And today I will introduce my recent work, Post-Information Assist 60 GHz Network. And this is a joint work with my advisor, Xinyu Zhang from the University of California, San Diego. The 60 GHz network has emerged as the next frontier wireless technology. And it centers at 60 GHz and can provide multiple gigabit per second connectivity. And the ultra-high bit rate can help supersede many traditional wire connections, such as the wireless backhaul. And they also can enable many demanding applications, such as the wireless backhaul, mobile-to-screen video cast, and untethered virtual reality. And since the 60G network operates at such high frequency, to compensate the signal attenuations, it adopts the phased array for directional transmission. The phased array comprises many small antenna elements, and they form a directional beams, which are electrically steerable. Even though they had multiple beams, but their joint coverage is still limited, which is known as the field of view, or FOV. And this problem is caused by two aspects. First, this is due to the intrinsic half-phase coverage of the patch antenna element. Second, the phased array can typically install on the one side of the mobile device. And the other side will suffer from severe attenuation due to the device blockage. For example, 60 GHz kits for wireless VR currently in the market is reported to have a field of view of only 160 degrees. So as a result, the current 60 GHz link is primarily limited to a point-to-point and stationary setup, and enabling seamless coverage and mobility support will be important for many applications, such as the wireless VR. So to understand the impact of the limit FOV, we conduct a measurement study using two commercial 60 GHz laptops. Both of them are running the 802.11ad standard. And one of them is configured as access point, and the other is client. And we rotate the access point central around the client and measure the bit rate at different directions. And we found when they are in each other's FOV, the link can achieve a very high bit rate. And the right figure shows the corresponding beam index during the rotations. And the radius, the active search for the best beam alignment. And when they are out of the FOV, we found the link can drop to only a few hundred megabits per second. And the difference can be up to 4 times here. And we also measure the link throughput versus the link distance. And we found the current 60 link can sustain a relatively high throughput, even up to 13 meters. So the above result indicates the device orientation is more critical than the device or the link distance for the 60 GHz network performance. So to address this problem, we propose a system which is called PIA, which can enable seamless coverage and mobility support for the 60 GHz network. Our basic idea is to deploy multiple access points at different corners of the room, so that no matter how the mobile device moves and rotates, it's likely to fall in one of the access points. However, the above architecture brings two new challenges. First, how to determine which AP should be used to transmit to the client. Second, with multiple access points, it's possible to transmit with multiple clients at the same time, but how to manage the interference across different links? To address these two challenges, we take advantage of the 5-degree freedom post-information available from the mobile device and devise two modules called AP selections and interference management to help improve the 60 GHz network reliability and capacity. And the post information currently is available from many mobile devices, such as the VR headset. So for the AP selections, the naive approach is just to let the client sequentially probe each access point and then find out the best one. However, owing to the large number of beam patterns, the probing will drop the bit rate. And we adopt a different design principles. That's to predict the best AP based on the post information. And to do so, we first modeled the FOV of the phased array antennas lie above. And then based on their pose information, we determine whether the client AP fall in each other's FOV or not. If is, and then we consider the link is good enough for high-speed transmissions. And to prevent the link from outage, we also predict the client's pose in short near futures. And based on the predicted pose, we determine which AP the client should connect to and when. However, the above basic design requires to know the AP's pose, which is typically hard to know because the phased array antenna is typically sealed inside the AP and its orientation is invisible to the end user. So to solve this problem, we incorporate a sensing stage before putting the network into use. So the sensing stage will take the 60th link measurement result, such as MCS active beam index at different locations, associated with the 5-degree pose informations, to estimate the AP's pose and the other information. So the challenge in estimating the AP's pose is that currently we only have the link level measurement as input. And the current commercial 60 wireless device cannot provide physical layer information like the phase. And to solve this problem, we propose a statistical pose searching algorithm. Our key insight in this algorithm comes from the previous measurement study. That's when the AP and client, they fall in each other FOV, the link can get a high bit rate, otherwise it's low bit rate. So we first let the user randomly walk inside the network environment and then measure the link state associated with different poles. And then the algorithm will statically search for the candidate AP post and then find out the one that minimizes the mismatch between the measured link state and the predicted link state. For example, the AP is unlikely at the right side because it causes a lot of mismatch, and the left side ones will best match. Recall that the 60 radio used the directional transmissions. So with multiple access points, it's possible to transmit to multiple clients at the same time without interference. And this property can enable many interesting applications, such as the multiplayer VR gaming, where each player requires and dedicate high-speed video streaming. However, we found the current beam patterns of the 60th phased array are not ideal yet. This figure shows the beam pattern measurement from the commercial 60th laptop. So ideally, each beam pattern should only point to one direction. However, we also find that multiple other directions also have relative large signal strengths. And there's two causes to this phenomenon. First, the practical phase shifter for current 60 phase array can only shift the phase value toward a limit set of angles. For example, in the radio we use, it can only shift the phase value every 90 degrees. So the cross phase shifting cannot generate a very ideal beam pattern. Second, we are using the OEM codebook for the phased array antenna. So the codebook is not specifically optimized for the 60 laptop. And the beam patterns can be affected by the nearby electronic components when the phased array is installed inside the mobile device. So the irregular beam patterns here will cause unexpected interference across different links. So to address this problem, we propose the post-assist spatial sharing mechanisms. The basic idea is just to predict the cross-link interference using the pose information. And to do so, we leverage the beam strength vector, or called the BSV, which is defined as the signal strength of all beam patterns in a specific direction. For example, the right figures, the x-axis here is the beam index, and the y-axis is the amplitude. So we will collect the BSV between each pair of access point and client, and form a map as illustrated in the right figures. And from this map, our algorithms will find the set of beam assignments that maximize the signal to interference ratios, which will maximize the network capacity. But again here, the model here only considers the interference from the line of sight. And in practice, the signals may be redirected by nearby reflectors and cause non-line of sight interference. And to solve this problem, we also incorporate a reflector sensing scheme, which is also a one-time calibration process. Our basic idea is to reverse engineer the reflectors by tracing back the signal angles. So we will first ask the user to randomly walk around the dominant reflectors, such as concrete wall and metal furniture in the environment. And to trace back the signal's angles, we leverage a key observations here. That's the measured BSV under multiple reflections becomes the superpositions of predicted BSV along different paths. So the predicted BSV here is the one that directly derived from the beam pattern. And we formulate the above observation into a linear algebra equations. And the measured BSV equal to the sum of the predicted BSV along n different discrete directions. Each times an associated weight. The weight denotes the channel gain. And a non-zero gain means there's a path along that direction. And owing to the sparsity of the 6-tier channel, there's only a few paths in the practical environment. As a result, the above equations can be efficiently solved using the compressed sensing technique. And with the signal angle informations, we can backtrace the signal's propagations and locate the reflector positions. And to model the reflector impact, we leverage the concepts of virtual AP, which is inspired by the 6-tier ray tracing model. So the virtual AP will be in a location that mirrors the real AP relative to the reflectors. And the virtual AP will be used in the same way as real AP in our optimization framework. And we implement the above systems in a free AP 6-tier network testbed. So each access point is installed with a commercial 6-tier wireless card and the commercial 6-tier phased array. And the access point is connected to a 10 gigabit Ethernet, and they form a 2-hop network as shown in the right figure. And to evaluate the system performance, we also extract the radio information from the drivers, such as MCS throughput and also the beam index information. And to get the pulse information, we attach a Tango tablet to the outer surface of the laptop. And we run the experiment in a lab environment, the size around 8 by 8 meter. In the sensing stage, we will first collect the training data of random walking over 15 meters. And the training data so take a user less than 1 minute to finish. And we use the training data to evaluate the accuracy of AP pulse sensing. So we found the AP's position error and orientation error both decrease as the walking distance. And if it's larger than 11 meters, the pulse error almost stabilizes at 0.3 meters and 0.17 radians. And the right figure shows the accuracy of compressed angle sensing, and its performance is primarily determined by the SNR of the BSV measurement. And we found the accuracy is, so the error is less than 5 degrees, even though the SNR is as low as 9 dB. And the residual error here is mainly caused by the angle discretizations in the compressed sensing algorithm. And we next evaluate the link state prediction accuracy, which is the key component in the AP selection. So the ground truth is determined by the link throughput. For example, if the link bit rate is dropped below 1.5 gigabit per second, but the system predicts it's a good link, we will consider it's a wrong prediction. So the result shows that the prediction accuracy is quite robust to the client's location error. It's because slight client location offset won't affect the relative FOV relation by much. The system is more sensitive to the client's orientation error. However, the practical mobile device, such as a VR headset, can only provide quite reliable orientation information. And for the system level test, we will evaluate the number of link degradations that defined as the link drop below 1.5 gigabit per second in a 5-minute random walking. And the no switch means there's just a single AP deployment case. And the soft probe means the client will try to probe a best AP if you think the current link degrades. And the hard probe case, in the hard probe case, the client will probe the best AP periodically. And the oracle case is the optimal case, which is just directly derived from the coverage of current AP deployment. And we found our scheme can reduce the number of link blockage by around 6.3 times compared to the single AP deployment, because it can actively switch the access point before the current link degrades. And we also evaluated the network throughput performance under the multiplayer VR scenario. And we found our post-assist spatial sharing mechanisms can improve the overall network capacities by around 83% compared to the AO2000 AD scheme, because it's jointly minimizes the cross-link interference through proper beam assignment. And to summarize my talk, in this work, we identified the challenge of robust connectivity in 6 GHz network. And we proposed the multi-AP network architectures and used the pulse information as the fundamental primitive to enable seamless coverage under mobility and orientation change. And our design components can enable agile link predictions and interference management. And we implement the system on a commercial off-the-shelf 6 GHz radio testbed and demonstrate significant improvements over the network reliability and capacity. And the design can potentially meet the needs of demanding applications, such as the wireless VR. And thanks for listening. I'm happy to take any questions.